Hi guys, Miss Marusik here, and in this video we're going to be talking about net ionic equations. Now hopefully we remember back from Unit 3 that we have certain substances that will dissolve and separate into ions. We say that they dissociate into cations and anions when they're dissolved in water. And so what happens is that sometimes those ions remain exactly the same from the reactant side to the product side. They don't undergo any kind of major change throughout the process. So a net ionic equation addresses the fact that we could take those ions out and show our equation without those spectator ions in them. And then that way we're only showing the actual change that's occurring in the solution, basically the driving force behind that reaction actually taking place. Now it does give us some guidelines on here about what kind of things we can break up and what kind of things we need to keep together. So of course ionic compounds will dissociate if they are soluble. So we might have to check these against our solubility rules. However, compounds that are solids, liquids, or gases do not dissociate. And so we want to leave them together when we undergo these processes. Now we are going to talk a bit about strong versus weak acids and bases. We didn't really deal with those in net ionic equations back in pre-P chemistry, but we are here, and so we'll talk about a few of those as we get toward the end of our video today. So we have kind of three new types of things that we're going to do in these equations. First off, we're going to write a complete ionic equation, which shows anything aqueous split up into those ions. Then we are going to have our spectator ions. These are things that stayed the same from side to side, and so when I write my final equation, I'm going to take those out. So then we have our final net ionic equation, which is only showing the particles that are actually participating in that product formation. They are the driving force behind that process actually occurring. So we are given an example here. We can see we have a double replacement occurring between potassium chloride and silver nitrate. And we went ahead and wrote our products here. And we noticed that one of those products ended up being a solid. And it's the formation of that solid that actually drives this double replacement to completion. So then in the complete ionic, anything that had an AQ was split up into its ions. You notice I did show them with the charge and I did show them with their state of AQ, but then I left that silver chloride solid precipitate together. And so then in my final net ionic, what I do is I look for anything that remained the same from side to side on that complete ionic. I see that I had potassium ions from side to side that stayed exactly the same, and I had nitrate ions that stayed the same from side to side. And so what those mean is that those are spectator ions. And so we did not include them in this final net ionic equation. All right, so we're going to run through several examples of these net ionic equations today. And we're also going to show a particle diagram for them. How could we illustrate these processes occurring? So we're going to take what we did in the videos from last class and kind of up our game a little bit. We're going to actually show substances dissociated in solutions. All right, so we have here zinc nitrate and sodium carbonate. And so what I'm going to do is I'm going to start off by writing my original equation. Okay, so zinc is +2, nitrate is -1, so I'm going to write ZnNO3 2 to balance out those charges. I'm also going to go ahead and put a state. Now with these processes, you would typically be told, hey, there's water present, or hey, we had some solutions present. So I'm going to assume that these were both starting off in solution. And I can also predict that based on my solubility rules. As we remember, hopefully, all nitrate compounds are soluble. And so that would have had that AQ with it. Okay, so then I'm going to have my sodium carbonate. Sodium is Na with a +1 charge. Carbonate is CO3 -2. So to balance those out, I would have Na2 CO3, and that would be aqueous as well because I have something in it that's in group 1. So now I'm going to do my reaction between these. And hopefully we recognize that we have a compound and a compound here. So more than likely I would do some sort of double replacement reaction. And so what that means is that now my zinc is now going to be paired with the carbonate. Now, when zinc and carbonate pair up, those charges will cancel out. So I'm going to put ZnCO3. Now, I know water's present, so there's a chance that this could dissolve, but I would need to check it against my solubility rules. And so I would kind of go through here and I would say, well, I don't have something in group 1. I don't have ammonium. I don't have nitrate, acetate, chlorate, or perchlorate. I don't have chloride, bromide, or iodide. I don't have fluorine. I don't have sulfate, nor do I have hydroxide. So when I get to that last rule down here, basically at this point, everything else is insoluble, meaning this guy would have gotten an S for solid precipitate. Now, my other pairing would have been the sodium with the nitrate, and those would too balance each other out charge-wise. So I'd have NaNO3. However, here I have both a group 1 and a nitrate, so hopefully we recognize that as being soluble. Now, I would need to go and balance from side to side. I can see I don't have the same count of things from side to side. I have 2 nitrates and 2 sodiums over here. So it looks like if I put a 2 in front of this NaNO3, that should fix my issues as far as the balancing is concerned. Now, I will tell you this. A lot of times on the AP test, they will go ahead and give you this balanced reaction automatically. So you would not have needed to write it. You would just need to then do the next steps that we're about to do. Or there's a possibility that they could have told you for sure, hey, one of our products was a solid. So even if you didn't have this chart available with your solubility rules, you could have said, well, hey, I know this one has a group 1 and a nitrate in it. So if I know I made a solid, then that means the only possibility for that solid would have been the zinc carbonate. So even though I use solubility rules on this, you might not have needed to necessarily have this chart in front of you to figure out what was going on here. All right, so the next thing I'm going to do is I'm going to write what we call a complete ionic equation. And what this does is it takes anything that would break up into ions in solution and show it broken up. So for example here, for this zinc nitrate, it's Aq, which means it does dissociate into ions because it was ionic to begin with. And if I think about dissolving equations back from Unit 3, I would say, hey, I have one zinc ion that was +2, and it would have an aqueous charge. And then it would also break up into 2 of those nitrate ions, also with an aqueous charge. All right, my next substance, again, is aqueous, again is ionic, so I'm going to show it broken up into ions. So I'm going to have 2 sodium ions and 1 carbonate ion. Okay, so now I'm going to move to the product side, and I'm going to go ahead and write this on the next row since I ran out of room. So now I get to the zinc carbonate, and I see that it's a solid precipitate in the solution, which means that it's not going to dissolve, and so therefore it's not going to dissociate into ions. And so therefore for that solid, I want to leave it together. I would also then have this NaNO3, but I can see it's Aq, it's ionic, so this would break up into ions. I would end up with 2 of these compounds dissolving, so therefore I would end up with 2 sodium ions, as well as 2 nitrate ions. So again, this is what we refer to as a complete ionic equation. I'm showing everything that would dissociate broken up into those ions. Now here's the deal. I have some things that stayed exactly the same from side to side. And when I say exactly the same, I mean both charge and state need to stay the same besides just the formula. And if I look here, I see that nitrate remained exactly the same from side to side, as well as sodium remained the same from side to side. So what that means is that those 2 substances are spectator ions. They're present for this solution reacting, but they themselves aren't participating in that process. They're just simply watching the reaction take place. So the last thing I'm going to do here is I'm going to write my net ionic equation. And when I write my net ionic equation, I would write it without those spectator ions. So anything that wasn't a spectator would get included here. So I would have my zinc +2, aqueous, my CO3 -2 aqueous, And then on the product side, I would end up with that zinc carbonate precipitate that we ended up forming. So again, this change here is the driving force behind this reaction actually taking place. If I had only made aqueous things at the end, so everybody ended up being aqueous, all the ions were dissociated, nothing would have really changed in that process, meaning that double replacement reaction actually would not have occurred. So the only reason this happened, the only reason it took place, is because of that formation of that solid precipitate drove this reaction to completion. Now, one of the last things we can do down here is draw a particle diagram for what's kind of happening in these original solutions as well as in the final product. So to start us off here, our first solution was the zinc with the 2 nitrates. So I'm going to put zinc ions and my 2 nitrates. So you can see this looks a whole lot like what we did back in solutions, where we showed our solutions broken up into the ions, so we showed them dissociated. Okay, so then my other beaker, I'm going to have sodium, and I'm going to have 2 of those, along with my 1 carbonate. Oops, I put the wrong charge there. There we go, we'll fix that. All right, so now in my final solution, here's where it gets kind of interesting. One of the things that you made was a solid, that zinc carbonate. I made that precipitate, which means that precipitate should be shown down here at the bottom, ZnCO3. Now, upon first forming, your solution probably would have turned really cloudy, and it really wouldn't have been all at the bottom, but if I let it sit long enough, that solid precipitate should all collect at the bottom. Now, up in the solution, I would still have my spectator ions present, just kind of hanging out. So as a reminder, my spectators were 2 sodium ions, and we'll try and get the right charge this time on this, and then as well as I had 2 nitrates. So there's what my solution would have looked like at the end of that reaction. All right, let's run through a couple other examples just so you can see a little bit of a variety on these. I do have these already written out just to save us a little bit of time. You don't have to wait for me to write all of these, but I am going to talk about them step by step. So looking at the ones on the next page. First, it said, hey, I have zinc metal and hydrochloric acid. Now, as far as the type of reaction here, I notice I have an element and a compound. And when we have an element and a compound, that means I have a single replacement reaction taking place. So keep in mind that you can actually do these net ionic equations for both double replacements as well as for single replacements. In both situations, we end up with those aqueous solutions that we could dissociate into ions. Now, I did one other thing here. I wrote that HCl is a strong acid. I'm going to talk about why here in just a moment. But once I decide that, hey, this is a single replacement, I would ask myself what zinc would pair up with. Well, I know when zinc gets in a compound, it becomes a positive 2. So that means I would want to pair it with the chlorine, but it would take 2 chlorines to balance out the charge on the zinc. And then that would end up kicking out hydrogen. However, hydrogen is diatomic by itself, so you notice I did have to put H2 there. And I know that hydrogen would be a gas at room conditions. So the next thing I would want to do is write my complete ionic equation. Anything that's AQ, I would want to show split up into ions. However, we leave solids and gases together as they are. So these would stay exactly the same as they are, but I'm going to change these 2 guys and break them apart. Now, the reason why it was important here to notate that HCl was a strong acid is because strong acids I will break up into ions. However, technically, if I had a weak acid here, because so much of it stays together, I actually leave it together in my overall reaction. So we'll see one like that here in just a little bit. So here's what I wrote. I wrote my zinc solid here. Then I had my HCl breaking up into 2 hydrogen ions and 2 chloride ions, both with AQ. Zinc chloride would break up into 1 zinc ion and 2 chloride ions, and then H2, the hydrogen gas, would be just the same as it was previously. Now here's what I would want to look and see what stayed the same from side to side. I see that the only thing that stayed exactly the same from side to side were those two chloride ions. And I know some people are like, well, wait, I have zinc by itself on both sides, but look at those states. They're very different on either side. Here also I have neutral zinc, and here I have zinc ion. So that's totally different. So my only spectator ion here were those chloride ions. So when I go write my net ionic equation, I would have the zinc solid plus the two hydrogen plus 1 ions that were AQ, making the zinc plus 2 ion that was AQ, and then that hydrogen gas that gets released out of the solution. All right, so to draw this, a particle diagram of what's happening here. Now, since the zinc was a solid, I kind of just left it at the bottom. I didn't really show it in a solution. And so what I would do is I would take that piece of zinc and combine it with HCl. Now, we did have 2 HCl's in my original balanced equation. And so what I went ahead and showed that I had 2 hydrogens and 2 chloride ions in order to maintain my mole-to-mole ratio here. So then on the product side, I have that zinc chloride in the solution that would split up into the zinc and the 2 chlorine ions. And then I show the hydrogen that would be leaving the container as a gas to give us an idea of kind of the process that's occurring there. All right, let's look at another one. The next one says I have sodium nitrate and potassium acetate. So I'm back to a compound and a compound. So I'm back to predicting that this would probably be a double replacement. So I'm going to go ahead and start off by writing that double replacement reaction. My sodium nitrate and my potassium acetate, both of which had group 1 in it, so those were both soluble. And then I would switch around the partners. The sodium would end up being paired with the acetate, so that would give me sodium acetate. The potassium would end up pairing with the nitrate, so that would give me potassium nitrate over here. However, I still had group 1s at the front of this, and having group 1s at the front means that they would both be soluble, and so I ended up putting both AQ over here. So here's the issue. In my product, I did not form a solid or a liquid or anything that would help to drive this reaction to completion. For double replacements, anytime both of your products are AQ, that overall process is no reaction. This reaction would not take place. Now, as far as the reason why, well, I know I didn't write a complete ionic, but think about what would happen. This would break into ions. This would break into ions, this would break into ions, this would break into ions. Everybody's just broken into ions. So to kind of think about this from a particle standpoint, if I start off with sodium and nitrate ions and potassium and acetate ions, and then I put them all together, I still just have all those ions at the end. I didn't really change anything or make anything new that would drive this reaction to completion. I just have 2 solutions now that are mixed together. And so that's why on double replacements, for them to actually occur, I must be making some sort of solid or gas or possibly liquid water in order for that process to actually take place. Otherwise, it just ends up being no reaction like this. All right, let's look at a few on the next page. So our next one here is nitric acid and calcium hydroxide. Nitric acid being a compound, calcium hydroxide being a compound, and so therefore I can guess that that would probably be another double replacement. However, here the H in the nitric and the OH in the calcium hydroxide would end up pairing together to make water. At first it looks like you make HOH, which I can just write as then as H2O. And that would be a liquid at room conditions. It is a pure liquid at that point and not a solution. So my other product would end up being the pairing of the calcium with the nitrate. And since calcium is positive 2 and nitrate's negative 1, that would create calcium nitrate CaNO3 2. That does have nitrate in it, and so I could predict that that was soluble in each other. So now, I had a strong acid and a strong base. And you're like, why did she bother with that? Well, I know if both of those are strong, that I'm going to break those up when I write a complete ionic equation. So I came down here and broke up anything that was AQ. So this guy got broken up, again, because it was a strong acid. 2 hydrogens and 2 nitrates, both with their charge and their state. Calcium hydroxide, I broke up into calcium and 2 hydroxides, both with AQ and their charges. And then I said, ooh, that water gets left together. Now I just realized that I forgot my 2 over here that I had up here. And so I would want to make sure to include that. And then I had my calcium and my 2 nitrates being formed from that aqueous solution here. So now look what stayed exactly the same from side to side. Let's pick out those spectator ions. I can see that nitrate stayed exactly the same from side to side. I can also see that calcium stayed exactly the same from side to side. So that would give me those 2 hydrogens and the 2 hydroxides both coming together to making those 2 waters. Now, since everything was 2 and 2 and 2, I went ahead and reduced those coefficients when I wrote my final equation here for my net ionic, and I just wrote H and OH become that water. Again, making sure to show my charges and my states here becoming that liquid water. So I just reduced down the 2, the 2, and the 2 on the coefficients. As far as my particle diagram here for this process, here I had my original 2 nitric acids broken up. Here I had my 1 calcium hydroxide broken up. And so then I end up making my 2 waters in the solution. But of course, I still have those spectator ions present. So I still have that calcium ion and those 2 nitrate ions swimming around in that solution as well. By the way, this is what we call an acid-base neutralization. Anytime I react an acid with a base and I end up creating neutral water, we call that process an acid-base neutralization. All right, I've got one last one down here for you. Now this one, we had nitrous acid and lithium hydroxide. So I started off by writing my balanced equation. Again, I had a double replacement here. So the H and the OH would pair up to make water. The Li and the NO2 would pair up to make LiNO2, lithium nitrite. Now here's the difference on this one. HNO2 is a weak acid. And if you think back to what we did with solutions, weak acids only partially break into ions. Most of it actually stays together. And for this kind of process, when I do net ionic equations, I'm going to actually leave those weak acids together, because in reality, less than 5% of a weak acid usually splits up into ions. Most of it stays together. And so therefore, on my complete ionic equation, I'm going to leave that together. So I left it together even though it had an AQ. So be careful on those weak acids. I did go ahead and break up the lithium hydroxide. So then I had my water and my lithium nitrate that got split up. Again, that had that group 1 in it that meant it was soluble. So then I looked to see what stayed the same from side to side. I can see that lithium was the only thing here that remained exactly the same from side to side. So therefore, that lithium ion was my spectator ion. And so then when I write my final net ionic equation, I would remove that spectator ion out, and I end up with HNO2 aqueous. So again, I left that weak acid together, plus the hydroxide ion makes water and my nitrite ion. Our solution here at the end, our particle diagram, I went ahead and just wrote HNO2 in my beaker. If you remember doing these beakers back in Unit 3, a lot of times we would write HNO2 4 or 5 times, and then we would write 1 H and 1 NO2 to show one of them had split up. Well, here, because I want to maintain my mole-to-mole ratios, I just made myself a note that there might have been a little bit of H and NO2 -1 ions in there. Because again, it is an acid, so it does partially dissociate, but the bulk of it is going to remain as that HNO2 together. So then my LiOH splits apart. And so then when I go to my product side, I end up with that water that I ended up forming, the lithium ions that were the spectators, and those nitrite ions that are in that final solution. All right, hopefully we're feeling good about doing a complete ionic equation, a net ionic equation, and identifying our spectator ions. If you have any questions or need any help, please feel free to email me. Bye, guys.